In this video, we'll be talking about point estimate and confidence intervals. So, as we mentioned before, that social scientists cannot directly research a population for the most of the part because they don't have the money, they don't have the manpower, and they don't have the time. So usually what we get is a sample. And also we talked about before that we cannot simply use the sample status to say that this status is the parameter of the population. For example, if we get the mean of a sample, we cannot directly say the population mean is this sample mean. So what are we going to do is we have to run some hypothesis testing. We have to, from a statistical perspective, to make a guess. Okay, making a guess is very important in the stats because most likely when we're doing hypothesis testing, there is not like something that 100% will happen. The most of the time we are going, what we do is to guess like how likely these things will happen. So a little bit short information about the probability. It is the number of times event can occur divided by the total numbers of possible outcomes. Okay, the possibility theory also talks about that the logical premises that form a set of predictions about the likelihood of a certain event or the empirical results that one would expect to see in an infinite set of trials. So the probability and probability theory is really important in the hypothesis testing. Later you will see that we use the probability theory to make a guess based on how confident we are. So we mentioned this one in the previous PowerPoints about the sampling error. The sampling error exists because that every time when you're going to pull out a sample from the population, you cannot make sure that you are pulling the exactly reflection of the population. Every time when you pull the sample out of the population, even you pull several times, so each time the samples are different from each other, right? So what we can do is based on those very limited sample, we can kind of properly guess what the population mean is. Okay, so here we just talk about the sampling error. Any given sample that can be drawn has its own mean or proportion. So it cannot directly be used as the population mean or proportion. So what we do is that we have to solve this uncertainty. So to use a term called point estimate to estimate where the population mean is. Okay, so what you get is you get a sample mean and use some kind of sampling strategies and statistical strategies to make sure that you have a good chance to guess the population mean, what the population mean is. Okay, so this point estimate is just as you can see, it has a term estimate, so you have to estimate a point. So for a sample statistic, so the most likely what we will be guessing is a mean or proportion. The mean is used in like a continuous variables, or proportion you could have even used in like a nominal variables, categorical variables, but most likely we are going to guess the mean. But in this PowerPoint, I will show you how to do this one in terms of the mean and also in terms of the proportion. Okay, so a procedure does exist for calculate a range of the values within the parameter of the interest midline. So this is also called the confidence intervals. Okay, so it's like a range that we calculate based on the sample mean or sample proportion that we can confidently say that, all right, here is a range, and I think, or I have a good reason to believe that the population mean or population proportion will be within this range. Okay, sometimes maybe I will guess wrong, but I will make sure that I have a good guess. That guess and that the range is the confidence interval. Okay, so the confidence interval is like a bubble that allows the estimate to be more flexible. right? So let's say if we have figured out our mean is 10, we cannot directly say that the population mean is 10, right? Because we have sampling error involves. So what we can do is that we set an area or set a range, and we say that there is a likelihood or high likelihood that the population mean will be within this bubble. Okay, so what do you do see here is like, for example, I have um, a sample mean that represented as x bar. So if this is like a number 10, we cannot say the population mean is 10, right? Because we mentioned there is sampling error. So we create a buff zone like this. It may be from 7 to 13. It must be symmetric. Okay, it may be from 7 to 13, or it may be from 8 to this to 8 to 12. Okay, or it could be like a 9 to 11. So the thing is that we create this buff zone, this range, okay, to 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 say that, okay, although I don't know what exactly the population mean is in this example, I know it may be equals to 10, but it may be not a 10. But I have a good reason that the population mean will be lying somewhere between 7 to 13 or 8 to 12 or 9 to 11. Okay, the whole process is called point estimate, and the buff zone is sort of called of confidence intervals. So we use the distribution. Typically, we use the Z and T distribution to make a good guess. And we talked about this before in the previous PowerPoints, is that if the data is large enough, over 100, most likely, we will be using the Z distribution, right? The Z distribution is a very standardized normal distribution. It has only one curve that can be used in large sample size. If it's a smaller, less than 190, 60, even like a 40, then we are going to use a T distribution, which is a set or a family of the distribution. They still be normal curve, but it's just look like a little bit different from the Z distribution. Okay, so here we just use those T and D distribution to figure out how likely it is that our confidence interval truly does contain the true population parameters like mean or proportion. So the probability that the internal interval contains a parameter is called the level of confidence. Okay, the level of confidence is the probability that confidence interval contains the true population parameter, mean or proportion. Now, traditionally, we set up a level of confidence at 95% or even 99%, right? 95% means like you are very confident, and 99% like you are super confident. So what does that mean? So if it's a 95% confidence, that means there is a 5 chance that the prediction will be wrong. And if it's a 99% of confidence, there is a 1 chance. So basically means like if I have 95% level of confidence, so which basically means if I make 100 times guessing about where this population mean is, 95 times I will be right. This true population will between those two numbers, or this confidence interval will be correct, and only 5 times that I got it wrong. And the similar can be applied to 99% level of confidence. That it basically means if I make 100-time guess, 99% or 99 times I will be correct. Only 1 time I will make something wrong, right? So as you see, like as a 99% confident interval has a greater chance than a 95% of being correct, but the 99% confident interval will be wider and less precise, which does kind of make sense. So for example, if I have this place here and I have the mean here, right? So I have the 95% confidence is that the true population mean will be here. Then that means 95% times I'm correct, 5% times I'm wrong. What if I want to improve my guessing to be more to have a higher correct rate? So if I want to be more correct or high likely to be correct, I have to make it wider, right? because if it's small, then sometimes like there are 5 chances that the population mean will be outside the confidence intervals. So I must make it bigger or wider so that I can reduce the times that I make it wrong. But again, simultaneously, when you make it wider, you're making it less precise, right? You make it less precise, but you can make the prediction more um, better. You can make the better prediction, but it's less precise. Okay, so here is that confidence interval should be selected based on whether it is more important for an estimate to be correct or to be precise. But the common thing we are going to, especially in the social sciences, criminal justice, criminology, we typically set up a 95% chance. Okay, 95% chance. That's what we typically do. But you also know that 99% chance is also possible. Okay, you will see 99% confident level of confidence in some of the articles, but the most widely used is 95% chance. So the alpha level is kind of opposite side of the confidence. So the alpha level basically means like um, what's the chance if I got it wrong, right? So the alpha level is basically 1 minus the confidence level, and it usually represents as a proportion. As you can see, the confidence level, we always use like a percentage to talk about confidence level because it's more easy to understand. Like I have 95% confidence. You say I have 90% confidence. I have 80% confidence. I have 100% confidence that something will happen, right? It's more easy to understand. But alpha level, we usually use a proportion to represent the alpha level at 0.05 or 0.01. And again, so if it's a 95% confidence level, then the alpha level is set at 0.05. If it is 99% confidence level, the alpha level is set up at 0.01. Okay, it's basically the same thing. It's just a little different way to say it. Now, the thing is, instead, you usually see most likely you are going to see the alpha level. Okay, and then when we're going to use the hypothesis testing, the 0.05 is usually like the cut point about the alpha level. Sometimes you will also see the 0.01 in some of the papers, articles, but the most common one you will see alpha level is 0.05, which makes sense because, like I said 2 minutes ago, that the common confidence level we use is 95%, which is 0.05 alpha level, right? So the alpha is never inserted into the confidence interval formula. This is very, very important. So I will mention this one more time when we go into the formula to calculate the confidence intervals. Okay, it's not you're not never going to insert 95% or 0.05%. You're using the alpha level to find the critical value in the T or Z table. Then you figure out what is the critical value at that particular alpha level. So another concept before we go into move further, and it is very important in hypothesis testing, is to figure out if the distribution will be a two-tailed or one-tailed distribution. Okay, so the two-tailed distribution basically has two tails. So one is from the positive side on the right, one is from the negative side on the left. Okay, it can go both ways. And in other words, in those distribution, numbers could be positive, like positive 10, or numbers could be negative, like negative 10. Okay, it can go like either way, have positive and negative numbers. For example, the classic Z distribution we mentioned in the previous PowerPoint is a two-tailed distribution, right? So the chi-square distribution, as you can see, it looks like it's very skewed, right? It's a positive skewed distribution. And you say it look like it has one tail here, right? So that means this is a one tail distribution, but that's a one way to understand a one tail distribution. You can also see that some people say, well, I do see a tail on the left look like a short one, but it's a tail. Um, So the another thing you can take a look at if it's a one tail or two tail, like I mentioned a minute ago, is that you take a look at if it has a negative number. So in this chi-square distribution, we are going to use this distribution in the later PowerPoint when we're going to do the chi-square test. You can see that chi-square distribution does not have a negative number, right? It goes to like a positive 20, positive 18. Those are very, very big, 6, 8, 4. But as you can see, it's on the left side, it goes stop with 0. Okay, it never goes to like this one, it goes to the negative side. No, okay, it never goes there. And you can tell from just from the name that it has no negative number. Where can you see it? Square, right? Every time when you see the square, it means when you're calculating whatever this is, when you're calculating something like that, you square something. When you square something, you couldn't get any negative number. Okay, so chi-square distribution is a one-tailed distribution, but you can see it's a highly positive skewed distribution, right? So the similar as the F-test, we will also talk about F-test when we're going to use or talk about the ANOVA test in the hypothesis testing in the future. But the F-test is also a one-tailed distribution. It has a long tail from the positive side, and it stops at 0. Okay, it does not have a tail on the left like going to the negative side, something like that. No, okay, it stops at 0. So it is a one-tail distribution. Okay. So now we are going to practice about find the critical value when we're going to do the confidence interval, or we call the point estimate. The very first we are going to do is to take a look at the z-curve, the z distribution. Okay, so because when we're going to talking about the alpha level means that sometimes we are going to make a wrong. So every time when we're going to make a right, everything will be in the middle, like this one. This part of the area under the curve is the one we are guessing right. And also the chance that we are guessing wrong, either it is too small, it's on the left side, or either it is too big, it's on this side. So if we say like we have a 95% confident, right? 95% confident. That means the alpha level is what? 0.05, right? Or 5%. So in this one, you can see that 95% or 9.95 is this area. Now we're looking for the 0.05 is those two areas. One is on the left, one is on the right because it's two-tailed. That is why every time you calculate the area here, we have to divide it by 2, because this part add together this part equals to 0.05. So they are symmetrical, they are identical, so you have to divide it 2. So which means each of the small area here is 0.05 divided by 2 is 0.025. That's the area here. So the area here is basically 2.5%. And also if we guess really, really small and we make it round, so the area here is also 2.5%. Okay, so this is the z-score table. We mentioned this before, right? When we're going to calculate the z-score in the previous chapters, we are going to do the way is that we set up a z-score. Let's say z-score is negative 3.44. Then we're looking at the area under the curve like 0.0003. That's the area here, right? So in today, what do we do when we're going to make a confident interval guess or a point estimate is that we reverse the process where we did the z-score calculation. So here is that I'm giving you the area under the curve like this one. I'm giving you area under the curve here, or giving you here, or even in somewhere here, and you tell me what is the z-score means. So how we do that? It's pretty simple. It's just a reverse process. So let's say the alpha level at 0.05. Okay, then we talk about that the p-value or the part of the proportion here and here, you have to divide the alpha level into by 2, right? So which basically means it's 0.025. So that means here is if I draw the picture like here, it's like this part supposed to be 0.025. Okay, so that is the thing you are looking for. You are looking for the number in the middle that is close to the 0.025. You can pause the video, find the 0.025 yourself. Okay, so where do we find it? So this is 0.025. We find that the 0.025 exactly there is a 0.0250 here, right? And then we take a look at the oh, cool. So it coming out like this is you combine this negative 1.9 together with the 0.06, then you get our D-score negative 1.96. See, this is like the reverse process compared to when we calculate the D-score, right? When we calculate the D-score, we give you the D-score, you tell me the area under the curve, like here. But now it's the reverse one. I give you the area under the curve here, you tell me what the D-score is. It's basically the same thing, but two directions, right? So if it's a two-tailed, then you will see like you will have the D both from the left side and both from the right side. The left side is a negative 1.96. The right side is positive 1.96. Okay, it's a pretty simple examples. So when you highlight this one, if it's the distribution alpha level at 0.05, so the lower one is negative 1.96, the higher one is positive 1.96. Okay, so again, what does this mean? This means that everything in the middle is 95% or 0.95, and the thing outside the middle, both left and right, if you combine them, that is proportion 0.05 or percentage 5%. Okay, we can practice another one. For example, alpha level 0.01. What do we do? So again, it's a two-tail. We have to divide it into two. So again, I put it this one here is that for this one part is supposed to 0.005, 0.005, right? So pause the video and find out where is 0.005 is. So let's take a look at the 0.005. Where is it? Okay, so this is a 1.0, the most close to the 0.005, like 0.0049, or you can also say this 1.0051, but usually I use this one, okay, 0.0049. So this is very close to 0.005, right? And then you will find out this is one negative 2.5 and 0.08. So you combine those two things together, that is negative 2.58 is the Z-score for the alpha level at 0.01. Okay, so since it's again it is two-tailed, so you are going to get a positive number, a positive 2.58, or a negative number, a negative 2.58. So and in here you can see that I can mark it alpha level 0.01. So the Z alpha negative side will be negative 2.58, positive side will be positive 2.58. So what does this mean? This means everything, the cut point here, everything in the middle is going to be, if we say in the proportion, that would be 0.99. If we say the percentage, that would be 99%. And anything that beyond beyond the middle, like to the right side, left side, there will be only 1% or 0.01 if you talk about proportion. Okay, now here is a conclusion for the Z-curve. It's very easy. Why? Because the Z-curve is always fixed, right? And also I mentioned before that in social sciences, the most common alpha level we use is 0.05. Sometimes we use 0.01, but most likely 0.05. So since the Z-curve is fixed, it only has one Z-curve. There is only one Z-curve. So the alpha level at 0.05 for the Z-curve, the Z critical or the Z number will always be 1.96, and the D of the alpha level of zero point zero 0.01 is always be 2.58. That means if you're looking at the Z table, you don't even have to look at the Z table, okay? When you decide that you can use the Z distribution, which basically means you are looking at a large data set that contains more than 100 cases. Those are the two numbers you will be using, okay, based on alpha level, 0.05 or 0.1. It's pretty simple, right? So what we have here, T distribution, is that very first time we want to calculate the degree of freedom. Now, typically the degree of freedom means in the stats, the number of degree of freedom is the number of values in the final calculation of the statistic are free to vary. Most likely will be the sample size minus 1. Okay, so for example, if the sample size is 36, the degree of freedom will be 35. That is the most likely you will see. But also, the degree of freedom in hypothesis testing may be a little bit different. Okay, that's a different thing we are going to talk about when we move into like a hypothesis test, a chi-square, t-test, ANOVA, correlation, something like that. It is different. But at this moment, this is just something you need to know. So the T table look like a little bit different. It's actually looking more easy compared to the Z table, right? The T table is very simple to tell you that the T table has, first of all, where the T is here, right? And also it gives you the 1-tail alpha level here or the 2-tail alpha level here. Okay, and on the left column, it also gives you the degree of freedom from 1 to like 100. And we mentioned this before because once you see it's getting larger and larger and it's super large, it's going to become a Z distribution. But in other words, the T table is very easy to read. It's actually more easy to read than the Z table. Okay, so we're going to make some example here. Let's say if the alpha level is 0.05, degree freedom of 60. So what is the area, or what is the number of the T? Not the area, but what is the T, the number, the value of the T? You can pause the video. Okay, so let's first look at if this is a two-tailed test. Then we two-tails, then we use the alpha level 0.05. We find that 0.05 here. Degree of freedom of 60. We find the degree of freedom 60 here, and move. You got 2.000. Okay, so this 2.000 is the T that we're looking for. Is a T value we're looking for. And again, since it's two-tailed, you have to understand that if it's a two-tailed, the T value will always be a positive number and a negative number, but their absolute values are equal, right? So in this case, the T will be positive 2.000 or negative 2.000. Right? If we make it into the T distribution here, and we set up alpha level 0.05, degree of freedom was 60, then you will see on the left side, it's negative 2. On the right side, it's positive 2. Okay. Now, again, the similar interpretation here is that everything in the middle under the curve, like here, since alpha level 0.05, that means those are the 95%. Or the 0.95 if it's a proportion. And the thing on the left side and the right side, you combine those two, these two will be 0.05 in proportion or 95% in percentage. Okay, simple, right? So let's practice several more, okay? So alpha level 0.05, degree of freedom of 20. What is it? So you will see the alpha level at 0.05 is here, 0.05, right? And degree of freedom of 20 is here, and what is the number? 2.086. Okay, so 2.086 is the number we are looking at. And also, again, this is a two-tailed test. So we go into the one on the left side, negative 2.086, and one going to the positive side, which is a positive 2.086. When we mark this on our graph is the alpha level 0.05, degree of freedom of 20. Then on you will see the negative side is negative 2.086. Positive side is positive 2.086, right? Again, whatever in the middle is 95%, 0.95 in proportion, okay? Whatever on the left side and right side is small part, this is 95, no, I'm sorry, this is 0.05 or 5%, okay? It's the same. So what if the alpha level at 0.01, degree of freedom 18? Now 0.01 to tell degree of freedom 18, here you figure out the number is 2.878. Okay, again, this is to tell the test, so the t will be a positive t, yes, a positive t like a positive 2.878 and a negative t like a negative 2.878. We mark this here, okay, positive side, negative side. Now this one, since we are looking at the alpha level 0.01, so which basically means whatever in the middle, like this area, everything here, that basically means this takes about 99% or 0.99 as a proportion, and the left side and right side, you combine them together, that is only 0.01 proportion or 1%. Okay. What about the alpha level 0.05, degree of freedom like 1000? Now, this is a time you don't really look at this one, because if the degree of freedom is 1000, this is very large data. The very large data is that we don't really often use a t to do that. What do we use? Yes, we use a z distribution if that's big, but we can still take a look at this one, okay? Because alpha level 0.05, we find out degree of freedom 1000, it's bottom, like really here. It is 1.962. It's very close to the z number, right? So the z number is 1.96. Right? If you take a look at the previous slides, you will see that the alpha level 0.01, the z will be the 1.96, and now the t is 1.962. It's very, very close. But again, it has two tails, so it's on the left side, it's a negative number, and on the right side, it's a positive number, right? So if we mark here, we will see that you will have the negative 1.962 and a positive 1.962. Okay, again, everything that in the middle, like from here, everything in the middle will be 95% or 0.95. Everything on the left side and right side will be 0.05 or 5%. So similarly, if we do the alpha level at 0.1, degree of freedom 1000, you will see it is 2.581. Remember what we have the z like for this point alpha level 0.01. Yeah, it's like a 2.58, right? 2.58. So it's really, really close. Now, this suggests one more thing is that if the sample size is going to larger and larger, eventually the t-table become more and more standard normal. So it will become more and more look like a z-table. Okay, so in this example, t will be two tail. Since it's two tail on the left side, right side, I'm just keep repeating the same thing, but you get it, right? So one more time, the t between those two numbers or whatever in the middle will be 0.01. I'm sorry, 0.99 or 99%. On the left side, combined with the right side, will be 0.01 or 1%, right? So the question is when we go into looking at the t-table or z-table is that when we look at the z curve, right? Remember, look at the title. I'm putting the t curve here. So the question is when we're looking at the z curve, if you go back to the previous slides, the z curve is that we don't really care about the z curve, like how to find those critical value of z, because if the alpha level at 0.05, then the z will be 0.05, the z will be, let's see, 1.96, right? If the alpha level at 0.01, the z will be 2.58. It's settled. It's never going to change because the z curve only has 1. However, for this t curve, then you have to first look at the alpha level, 0.01 or 0.05, and take a look at the degree of freedom. What is the degree of freedom? And then use this table, the previous table, to figure out the critical t value. Okay, so there are some extra steps. So if we replace this with the z curve, then there might be 2 steps. One is the alpha level. Second is decide what the t score is, or the z score is. I'm sorry. But for the for the t curve, then we have to also take a look at the degree of freedom. Okay. So in this PowerPoint, I will show you 3 confidence interval you will be using in the future, or you can see those in like the papers as well, right? The first is the confidence intervals for means with large sample. You are using the sample mean to guess the population mean in a large sample. That means the sample size is larger than 100. The second one is that you are going to use the sample mean to estimate the population mean in a smaller sample, which is less than 99. And the last one is the confidence intervals for the proportion, even the percent. Yes, we can do the confidence interval for the proportions for categorical variables, although you don't really see this quite often, but yes, we can do that. So let's do one by one. Okay. So the confidence interval for the mean with large sample size. When we're going to talk about large sample size, undoubtedly we are going to use the z distribution, right? So the formula will be confidence interval equals to the mean plus and minus this part. Okay, this part, in other words, it has other name. It's called the margins of error. So this part is basically what we calculate is the bubble, the buff zone. Okay, so if you still remember the previous one, we have the x bar, the sample mean here, right? It's a number. It's a settled number. Okay, then this margins of error calculate is the upper boundary and the lower boundary. So it's like it's calculating where the bubble is, okay, from here to here. Because since it's identical symmetric, so you just need to calculate on one of the positive, or either positive or negative, and it's a symmetric, so the upper boundary here will be identical to the lower boundary here. They should have the same absolute value. Okay, so when you see this model, it's very, very important to remember that this is a very easy one, right? This is the alpha, the critical value, and this is the standard deviation of the sample. This is a sample size minus 1, take a square root, divided, and use the standard deviation divided by the bottom one and multiply by this is the critical. So again, very, very pay more very, very carefully that this d alpha is the critical value of alpha, not the value of alpha. Okay, so in the previous example, this is never could be, or sometimes maybe, but never could be 0.05 or 0.01. This is the z value you're looking for based on the alpha level. 0.05 or 0.01. So if it's a 0.01, that's 1.96. If it's 0.05, that 0.01, that it will be 2.58, right? It's settled. We talked about this like 10 minutes ago. Okay, so let's practice one. So if you take a look at the mean is 28.25. Okay, in this example, mean is 28.25. You wanted to guess where the population mean is. The first thing you take a look at is, oh, cool, large sample size. Large sample size means we are going to use the z distribution, right? And then you are looking at the alpha level 0.05. Oh, cool, we are going to use a 1.96. So what you do is that you put everything here, and I didn't show the process, but you can use your calculator on your phone and to double check this one. So you just replace those letters with those numbers here, and make sure that the alpha will be like a 1.96 here, and you do all the calculation, and you will eventually figure out that this margins of error will be equal to 12.23. Okay, that is where the buffer is. So that is like this is the mean. This is upper boundary, lower boundary. This is where those boundary is. Okay, so once you use the mean plus this margin of error, you will get the upper boundary 40.48. If you use this mean to minus this margin of error, you will get the lower boundary, that's 16.02. And this is what the mu is, what the mean of population, right? So the most important thing is that you have to understand that, like, we want to use a plain language to interpret the results to people that who don't understand stats, but they do really want to know what that is, right? So from this example, we say that, okay, so I have a sample that look like that. Then I have a 95% chance that or confidence that the true population mean mu lies between 16.202 and 40.48. Okay, so if I say this, that means I have 95% confidence, right? Because the alpha level is 0.05. That means if I make 100 times guess, 95 times guess, I will be right. 5 times I could be wrong. But this is good enough. Okay, although I don't know what this mu really is, I cannot know what the mu is, but I'm pretty sure that I'm super confident that the mu will between those two numbers. Okay, I couldn't know the exact number of the mu, the population mean, but I know it will be within those bubbles, within these bubbles. Okay, and I have a 95% chance that make it right, or guess right, and I have 5% chance that guess wrong. Okay, now, so another one, we have the similar thing. So you can see those two difference, right? The difference is that we set up the alpha level at 0.01. Okay, so if we use a setup at 0.01, what do we guess here is the alpha here will be 2.58, right? It doesn't really change because it's a z distribution. And you replace all the letters in the formula with those numbers and pull out your calculator, do the calculation. You will see this part of the margin of error will be 16.10, 16.10. You use the mean to plus this margin of error, you will get 44.35. Use this mean to minus this margin of error, you will get 12.15. And this is where the population mean is, right? So here, since the alpha level at 0.01, so our explanation or plain language is that there is a 99% chance that the true population mean mu lies between 12.15 and 44.35. Okay, now compare this one to this one, you can see that the range become bigger, right? The range used to be 16 to 40. Now it's become bigger. It's 12 to 44. That fits the thing we talked about at the early slides in this PowerPoint, is that if you want to make sure that you have more confidence to guess it right, you have to sacrifice the precise, right? You have to sacrifice that. You have to make the bubble bigger so you can be more correct. Okay. So what if the confidence intervals for the means with the small samples, the sample less than 100 most likely? So you can see that for the small samples, the one thing we change is that we're going to use the t distribution, and the formula we get is the same. Almost the same. The only thing difference is this T alpha is different. Everything else is the same. The mean, the standard deviation of the sample size. The only thing is the critical value, T critical value based on the alpha. Now in the past, when we have the larger sample, we use the Z alpha. Now we use the T alpha. Okay, that's everything else is the same. So for the T, you have to use the table to look at what the T alpha actually is in each of the calculation. Because for the z, it's always settled at 0.05 or 0.1, but the t, it could vary based on sample size. Remember when we practiced finding the t critical value in the previous slides, one of the most important thing we're looking at is the alpha level and the degree of freedom. The degree of freedom is really based on the sample size. Okay, so I'm not going to show the complete things, but you have to practice it by yourself. But you see, like if I give you the sample like this one, and you first look at, okay, it's a small sample size, right? It's a small sample size, so what do? We have to use the T alpha. Then everything else will be the same. You just replace those letters with the numbers in here, and make sure you use a table to find the T alpha. Not the alpha, but the T alpha. Again, one more time. Okay, not the alpha, but the T alpha. And then you plug those T alpha here, you will calculate the margins of error from this confident intervals, and you will see it's a 3.26. Now you can do this practice by yourself and use a computer calculator, and also could use the tables in the previous one. Then you will see like the upper boundary again is the mean plus margin of error. Lower boundary is mean minus margin of error. That's the population mean. So here, one more time, there is a 95% chance that the true population mean mu lies between 31.74 and 38.26. One more time, I don't know what exactly the true population mean mu is. Okay, that's very important. You can never know what the true population mean is. But what's important here is that I'm pretty sure 95% chance, 95% confidence, pretty sure this population mean will between these two numbers. Will in these bubbles here. Okay. Similarly, you will have to practice the same thing. I'm not going to repeat it, but again, very first thing is take a look at the n. Is very small. Is a small sample size, so you are looking at the t distribution, and use the t table to figure out the t alpha. What is the t alpha? And once you figure out the t alpha, you can easily calculate this part of the margin of errors. It would be 3.94, and then you calculate this boundary. Okay, again, the very common language to explain this thing, 99% confident interval, is there is a 99% chance that the true population mean mu lies between 24.59 and 32.47. Okay, again, I don't know what is the true number value of the population mean mu is, but it would be somewhere between this one, and I have a very good chance, 99% chance I will be right. Only one time, if I guess 100 times, only one time I will be wrong. Okay, so the last thing for the for the PowerPoints is a confidence interval for the proportion, or sometimes percent, but most likely for the proportion. Okay, so the principle that guides confidence interval around means also apply to the confidence intervals around the proportions. What changes is that confidence interval for the proportion often use the z distribution. Okay, the z distribution is very safe if a sample is large and also contains 5 succeed-side variants. As long as you can see, if it's really a little bit large, then the z distribution is very safe to do that. Okay, we don't really quite need the t for the confidence interval for the proportion. So the formula you can see is different. Okay, so we use the z distribution formula, look like confidence interval. This is p hat. One more time, the p hat means the proportion in the sample. Remember, p hat means the proportion in the sample. The critical z value based on the alpha level. This is a p hat multiplied by 1 minus p hat divided by the total sample size. Take a square root of that and multiply by the z critical value. Okay, and one more time, since we are using the z is settled, it's only one curve, so the critical value of alpha here is very settled, just like the previous when we doing confidence intervals for large sample size is that if alpha level at 0.05, the Z alpha here will be 1.96. If it's 0.01, then it will be 2.58. It's settled and no other numbers because we are using the Z distribution. Okay, so if you practice this one, you will see it's very easy. This is larger sample size, over 100, right? The p hat, whatever the p hat is 0.50. So 0.5, and you use this formula, and again you calculate the margins over here, whatever here is, then you will get this margin over here is 0.08, and you use the p hat. Okay, you use the p hat 0.05. I'm sorry, not 0.05, 0.5 to plus this margin of errors to get the upper boundary, or to minus the margin of the error to get the lower boundary. So what does that mean? This is 99% confident interval. So there is a 99% chance that the true population proportion lies between the 0.42 and 0.58. So for the number, it's look like I can't really get what you mean here. Now let's say you have a sample of students. Okay, you have a sample of students like 380 students, and the male students take about 0.50. So female students takes about about 0.50, right? But again, you know that if you get a sample that has a male and a female students, the male students is take the proportion 0.50, female students take the proportion 0.50. It doesn't mean the population is half too. Okay, remember we talk about this sampling error thing is that if you have a sample that has half female, half male, it doesn't mean the population is just half female, half male, right? So what is the population proportion could it be for the male student? Okay, I don't know, but I can calculate the buffer zone. The buffer zone is 42% to 58%. That means if I have a sample that the male students takes half of the sample, then it means like I have 99% chance or 99% confidence to say that the population the male students takes about 42 to 58%. Okay, that's the simple way or a more understanding way to interpret this proportion. Okay. So the similar thing for another one, just for another practice, you can also use a calculator to do this one. Again, what you see is that the alpha level 0.05. So what you're gonna do is you replace this one with 1.96, right? And then you replace all the letters here, and you will get this margins of errors here, and go into the margin of errors, become 0.04. You use the proportion, added this one, you get the upper boundary, minus this one, you get the lower boundary. So the explanation will be there is a 95% chance that the true population proportion lies between 0.84 and 0.92, when the sample proportion is 0.88. But the population proportion is because we don't know, but we know there is a 95% chance that the population proportion will be somewhere between 0.84 and 0.92. That's it.